Hello everyone, my name is Berkehan Tatli and I'm a master's student at Department of Aerospace Engineering of the Middle East Technical University. Today I'm going to present you about the strain gradient plasticity effects on the modeling of hydrogen-induced failure in polycrystalline metallic materials. Here's my outline. I will start with my motivation, then I'll continue with the mechanical modeling, give a brief introduction on the constitutive models, failure framework, numerical implementation of this coupled framework, and I will present my numerical results and give my conclusions and my outlook on the topic. To start with, hydrogen is known to be a good candidate for a future energy resource, but it has been known over 100 years that it has caused catastrophic failures of metals. Hydrogen embrittlement, as we all know, is a reduction in the ductility of a metal due to the absorbed hydrogen. It mainly diffuses into the steel, relocates itself into the crystal lattice, and just causes fracture even under the 1/10 of the fracture toughness values. The primary failure mechanisms found in literature may be summarized as the hydrogen-enhanced cohesion, hydrogen-enhanced localized elasticity, hydrogen-induced phase transformation, and novoid coalescence. In my presentation, I mainly focused the failure mechanism of hydrogen-enhanced cohesion and to illustrate the effect of strain gradient crystal plasticity on this failure mechanism. For this purpose, I have inserted cohesive zone elements between the grain boundaries. I implemented the stress hydrogen diffusion model and the crystal plasticity strain gradient crystal constitutive models into the framework. To give a brief overview about the constitutive models that I used in the study, I'll just talk about the strain gradient part. In our group, we just derived it from the crystal plasticity local one and just introduced a total slip resistance by including the GND slip resistance. The equations can be seen in this slide. So the model parameters are also included with the length scale parameter, as we have non-local framework with strain gradient crystal plasticity. The failure is implemented within grain boundaries by cohesive zone elements, and I used potential-based cohesive zone model, the PPR. We have 8 model parameters to be defined: the critical cohesive strength, energy, shape parameters, and initial slope indicator. And illustrative figures can be seen on this slide that the thickness of the cohesive element initially is 0 and just deforms according to the TSL law that we define. The coupled framework can be summarized as can be seen on the figure. First, the finite element solver provides us with the displacement and the strains. We just provide the UMATs for the constitutive model of strain gradient crystal plasticity, and the UMAT HT subroutine is solved for stress assisted impurity diffusion, that we mimic the equations of the heat transfer to be compared with the stress assisted diffusion equations, such that we can use UMAT HT in this software abacus. And we calculate the hydrogen surface coverage and correlate the cohesive strength or cohesive energy with high surface coverage of the hydrogen, such that the traction separation law inputs can be degraded based on the hydrogen concentration values. First, I'll try to verify my model in a 2D case. I've used the experiments from 2005, the node specimen and uniaxial tension loading case. I've just modeled it in my software and inserted cohesive zone elements in between, in the middle of the specimen. And I've just changed the initial concentration values of the hydrogen and just resimulate for 10 or 20 of them. The y-axis is sigma NV, means the maximum force observed in the simulation, and the denominator means the initial cross-section area of the specimen. I've got a good agreement with the experiment, and by the way, the blue curve is also a simulation results obtained from 2018 paper of Emilio Martinez Panetta. Our model is also working good from this figure, and I'll continue with the polycrystalline example. In this example, I've just generated 50 grain case with a mesh of around 10,000 elements and 2,000 elements of cohesive elements. On the right, you can see the cohesive zone mesh that I've generated with in-house generator code. And on the left, you can see the geometry of the 50 grain polycrystal. Here are the boundary conditions of our cell. We just try to keep the stress axiality constant at 1/3 the uniaxial tension value. For that, we just couple the master node with right, top, and front, and left. So the remaining surfaces are just kept fixed at their respective directions. The initial condition value, initial condition is defined for the hydrogen concentration, and also the right, top, left, and bottom surfaces are fixed in the hydrogen concentration to keep numerical simulation stable. Here's my numerical parameters, the model parameters I've used in the simulation. Just to remind you that the hydrogen-induced degradation is made possible by the degradation of the cohesive energy, not the cohesive strength in this case, different from the macroscopic example. And here are the results. As expected, as the hydrogen concentration increases, I've got a decrease in the stress strain response. But with this local model, the crack path didn't seem to be changed. The non-local results is a bit interesting to check, because as the hydrogen concentration increases, the crack path also changes in this case. Just to compare the local and non-local results all together, as we expect when we introduced the internal length scale parameter, the stress and strain response just increased. As we continue, I want to show you the formative stress contours. As expected, the internal length scale parameter, I mean the non-local results, give a higher stress strain response than the local one on the left. But the crack path didn't change in this case. This is the results for hydrostatic stress with comparing the local and non-local models. In this case, hydrostatic stress seemed to increase a bit more, not a bit, and more than the local case, which replicates the experimental findings better in that sense. And when we continue with the initial hydrogen concentration of 0.5, the results are a bit interesting, as the crack path is also changing in this case with local and non-local case. And again, as we expected, the stress concentration is increased in non-local model with the introduction of internal length scale parameter, and the hydrostatic stress again is higher than the local model. Then the hydrogen concentration contours, as we can see, just before the unloadings occurring in the model, hydrogen concentrates more on the local model than the local model. And we continue with the hydrogen concentration value of 1. Again, the crack path will be changed, as you will see, and it will occur in a completely different section of this geometry. That's interesting. Maybe it will be due to mainly the hydrostatic stress change observed in this simulations because of the non-locality. This is again hydrogen concentration contours. Again, we can observe that the concentration increased just before the unloading state for the non-local model. And I've just compared the GND density results in non-local models with increasing hydrogen concentration. And I observed that the GND is more concentrated for a no concentration case. This is because as the hydrogen concentration increases, the cohesive strength, cohesive energy is reduced such that the unloading is occurring more than the other case. So the stress accumulates less than the hydrogen-less case. That's why the GNDs are more accumulated for the hydrogen concentration is 0 case. And I just tried to compare the results with larger grain, smaller grain size. And I increased the grain number to 350s, and with this mesh and the cohesive zone elements. The results are again compared based on the true stress and strain. As you can see with the local model, the straight lines are belonging to the local, and the dashed lines belonging to the non-local model. As the grain size changes, the local model cannot capture because this side of the curve is on top of each other almost. But as the grain size changes for non-local model, we can capture this effect. So maybe it's still better to get the experimental data with the non-local models. In this case, the formative stress contours also showed a slight increase in the stress, but a crack path change for the change in local and non-local models in between them. As we can see, the downside of the crack changes. This is the hydrostatic stress contours. Again, as the non-locality increases, the hydrogen concentration increases such that hydrostatic stress concentration is increased due to the effect of the increased overall stress. And this is the hydrogen concentration contours for local and non-local models. And as you can see, just before downloading, again, for the non-local model, the hydrogen concentration increased, and it changes the crack path completely, not completely, but a bit. To give my conclusions and outlook, we just implemented the strain gradient crystal plasticity models to deduce some results based on the hydrogen enhanced equation mechanism, and to check the effect of non-locality on stress concentration, hydrogen concentration, and hydrostatic stress accumulation. Our preliminary results indicated that the non-local effects may play a crucial role in micromechanical modeling of hydrogen-induced failure, as we observed size effects significantly increase the stress accumulation near the grain boundaries, and it caused the buildup of because of the build-ups of the GNDs, and this changed the crack paths especially for the high hydrogen concentration values. The use of strain gradient crystal plasticity also, I said, increased the hydrostatic stress concentration near the grain boundaries, especially just before the unloading state. But still, it's some kind of a preliminary results, and we should try to check the microstructural parameters such as morphology, grain misorientation, texture, grain size, and or also initial hydrogen concentration, to examine the effects on the microscopic failure and the microstructural evolution of the RVs and the polycrystalline materials. Thank you for listening. I would be glad to answer your questions.